afternoon. So, hi Srishti. Hello guys, good afternoon. Hi Priyanka. So, ಹೇಗಿದ್ದೀರಾ? Good afternoon. So, hi Vinay. Hello bro. Good afternoon Priyanka. Good afternoon. So, guys, I hope I sent you the electrostatics DPP3, which is for Gauss Law and electric flux. In today's early morning, I sent that in your WhatsApp group. Also, it's updated in your notes. Please check that. So, hi, good afternoon, Samarth. So, hello, hi, Saila Hari. Hi, YouTubers, good afternoon. So, hope everyone is doing great. So, I had shared, YouTubers, I was telling this, an update. So, it was about the DPP1, DPP3 for electrostatics is shared in your notes, class notes. Please check that and try to solve all problems, guys. So you could let me know if you have any difficulties in solving any problems. You can ask me to share that by yes. Thanks whoever did this. Thank you. I like this Rangoli. Okay, so what should I do with this? Annotate, erase. Annotate off. ಯಾರು ಮಾಡಿದ್ದು ರಂಗೋಲಿ ಚೆನ್ನಾಗಿತ್ತು ಎನಿವೆ that always helps me remind that yeah, I should turn off that. Thank you. And again guys, so ಚೆನ್ನಾಗಿತ್ತು ಒಳ್ಳೆಯದು. So guys, please take the technical check. So ನೋಡೋಣ. Let me know if my voice is audible to everyone clearly and the screen is visible to everyone clearly. Hi Krish Modi, good afternoon. Hi Sahil Hari, good afternoon. Cool, thank you. So yeah, please everyone in Zoom, please you have to respond using a poll. Okay, if my voice is breaking or if my voice is getting low, let me know. Okay. Yeah. Okay guys, so we'll start exactly by sharp 3 p.m. Yes, it's 3 p.m. And everyone who are available here, please take the oath of your technical check. Ellaru technical check tagoli. Hi guys, good afternoon. Yes, thank you. So guys, yep, come on, let's start our class. So I'll be yes, it's notified that I am audible to everyone clearly and the board is visible to everyone clearly. So I'm going to end this poll. Thanks for this. So guys, in our previous class, we had studied about electric flux. Just let's have a small revision. So we started with electric flux in our previous class. What is electric flux, guys? Please help me solve. So please help me complete the syllabus. Try to be active. Try to answer all the questions. You could help me solve all problems which are available today, and also support me with this. Let's try to complete. Okay. So please tell me, what is an electric flux? What is the electric flux? One word answer or two word answer is fine. Everyone in YouTube and also in Zoom. What is an electric flux? Yes, Anusha. Can you try to modify that answer for electric flux, please? Yes, correct, Samarth. Samarth, super. So electric flux means, say it's the number of electric field lines passing through a given area, passing through a given area. So in general, it's given as number of electric field lines times area. So mathematically, it's given as phi E. It's represented by phi. Electric flux is represented by phi, and it's given by phi E is equals to electric field, the strength of electric field times area. Okay, it's not a cross product, it's a dot product, E dot A. Okay, it's always a dot product, not a cross product, it's E dot A. Okay, let's everywhere try to write E dot A. So guys, next, so if I want to find electric flux for, okay, this formula, phi E is equals to E dot A, or phi E equals to EA cos theta, right? EA cos theta. So where theta is the angle between what and what? What is the theta? So guys, here, what is theta? What is theta? Theta is the angle between dash and dash. Fill in the blanks. So theta is the angle between, yes, correct. Priyanka, Bhargav, superb. Yes. Anusha, try to again ಇನ್ನೊಮ್ಮೆ. So electric field ಬಗ್ಗೆ ಮಾತಾಡ್ತಿದೀವಿ, electric flux ಬಗ್ಗೆ ಮಾತಾಡ್ತಿದೀವಿ. We are talking about electric flux. So try to give answer with that respect. Okay. So yes. Yes, correct, Bhargav, correct, Priyanka. So my theta is the angle between, it's the angle between, so my electric field and the area vector, direction of area vector. Actually, it's the angle between electric field and direction of area vector. My direction of area vector is n cap. So we had seen that. So to calculate the flux, we had to consider, say, if I have any given area A, then I have to consider its area vector always along normal, right? If I have any area A, I have to consider my area vector always along normal. So this we had studied. Yes, correct, Samarth. So again, so my flux now can be given as flux is equals to phi is equals to, say, this condition. This is for uniform electric field, right? So this expression, this is for uniform electric field. Say if I have a varying electric field, how can I write my flux? If I have a varying electric field, how can I write my flux? What should I do if I have a varying electric field? My flux, if I have my varying electric field, flux is given as, yes, integral of area E dot dA. Say if my area is varying, yes, correct. So if my area is varying, I should do the integral of area. If my electric field is varying, I should do the electric field of same integral, but electric field will be my function. So we have to take the electric field as a function and integrate with the given area. Okay, this was the second step, second thing which we learned. This is for non-uniform electric fields or non-uniform area. So it can be electric field or non-uniform area, both. Okay, next, third thing. So third, we observed, so we try to check out for Gauss's law. What is Gauss law, guys? What happens in Gauss law? Why do we require Gauss law? So what happens in Gauss law? What is Gauss law, or why do we require Gauss's law? Yes, correct, Bhargav. So we require Gauss's law for calculating or simplifying our electric field derivations. So in our earlier classes, we had derived expression for electric field, right? We had derived expression for electric fields. So using various integration methods, but here Gauss's law would help us to simplify that. Okay, so how would Gauss's law help us in calculating the electric field? So we'll see that today in applications of Gauss's law. But before that, let's give what is Gauss's law. So Gauss law gives talks about the flux, right? It talks about the flux in a closed surface. Gauss's law talks about the flux in a closed surface. Say if I have q amount of charge in an enclosed surface, then the flux is given as q upon epsilon naught. Correct, Bhargav? Priyanka? Right. So this is my Gauss law. Okay. So to apply Gauss's law, how to apply Gauss's law? We had studied two conditions for application of Gauss's law. What are the two conditions? Two conditions to be considered. What are the two conditions to be considered? First condition is, yes, I should consider my area vector dA. My area vector dA should be such that my electric field is uniform through it. I should consider an area vector dA such that my electric field should be uniform through it. Second condition was, I should consider my dA such that it should be a symmetry. It should be a symmetry. Why? What happens if it's a symmetry, guys? Try to help me. Tell me. Yes, correct, Ramakrishna Reddy. To find the net flux inside a enclosed surface is the right answer. So why? Why do we require symmetry? Yes, we require symmetry because, say, in any closed surface, if you remember in our previous discussion, we had considered a sphere. How many of you remember this? We had considered a sphere, a solid sphere. So what happens when we consider a solid sphere? I know there is charge distributed throughout the sphere. Now I considered a small area dA. Okay, guys, one more. So when I consider a closed surface, where is my direction of area vector? In this case, what is the direction of my area vector? Yes, Shailaja, correct. And yes, please, guys. Others try to, yes, correct, Dhanush. So it's always pointing outwards. My area vector always try to point outwards when we are considering a closed surface. Yes, the man. Yep. So why do we require dA as a symmetry? Again, coming back to the same question, why do I require my dA as a symmetry? Anusha? Amit? Dhanush? Someone try to answer? So anyone can answer, guys. Come on. Guess at least. So why should I consider my dA as a symmetry always while calculating the expression for electric field using Gauss's law? Okay, no idea. Rakesh, I don't know why you clicked on no. Yes, dA is the area vector. Why should I consider it as symmetry? Because to eliminate my cos theta. How? Say if I consider a symmetry, see if I consider a charge, say I have a sphere here, right? So I'll consider a charge inside my sphere. Say my charge is having a magnitude of q. Now this q emits electric field in all directions, right? So this q emits electric field, or the electric field because of this positive q is along all the directions. Now what is my theta here? If I have considered this dA, vector dA in a symmetry, so it's symmetrical all over, so I can integrate it easily. Now if I consider, yes, if I consider this, what is my angle here, guys? What is my theta here? Please tell me, please reply. What is the value of theta in this case? So we studied that my theta is nothing but the angle between electric field and area vector. So yes, correct. Guys, I need more participation. Please answer. My theta will be 0 degrees. Then what will be cos theta? What will be cos theta then? Why did I require cos theta? See, that's my phi flux. E dot A, EA cos theta. So to eliminate cos theta, I am taking this dA as symmetry. Okay, so this is much of the basics which we had learned in our previous class. So hope everyone knows this. So please remember this Gauss's laws, very basic definition. So any doubts in these guys, please ask me if you have any doubts. Yep. Yes, correct, Ramakrishna Reddy. It's theta 180 or 0 degree. Correct. So yeah. So please ask if you have any doubts in this. If not, I'll ask a question. I'll ask the question. If you confirm you don't have any doubts, I'll start asking question. I mean, I have only one question. I'll ask that. If you answer that, that's good. Yes. Okay, we shall proceed to the question. So the question goes like this. So everyone, please check the question. The electric flux through a closed surface, closed Gaussian surface, depends upon. Select your appropriate option. So everyone in Zoom can vote in your MCQ. Select your answer. So Manohar, check your answer. So everyone in YouTube can reply your answer as options A, B, C, or D. Okay, right. So you should know, to answer this question, what should you know? You should know the basic definition of Gauss's law. That's it. Yes, correct, Ramakrishna Reddy. Correct, Krish Modi, YouTubers. So here, yes, I have received plenty of answers, and out of 9 responses, 5 are correct and 4 are wrong. Come on, guys, you could give more response. So I'm giving you 30 more seconds to answer this question. Please try to answer. Bhargav, correct. Amod, correct. Shailaja, check your answer. YouTubers. Okay, guys, so I'm going to end the poll here. So the majority answers which I received was option C. So do you think option C is the right answer? Yes. Awesome, guys. Cool. How many of you think option C is the correct answer? Please click on S. You could give me the second time vote. In your participants, you could click on S. In your participants, you could go there. You could see tick mark S. So how many of you think C is the right answer? Okay, Latish, hi. So yeah, Latish thinks it's different. Okay, cool. So guys, yeah, let's come to the explanation part. So what is Gauss's law? Gauss law, expression for Gauss law is given by phi equals to the amount of charge enclosed in the closed surface divided by epsilon, right? Divided by epsilon. So this is my Gauss's law. For any Gaussian surface, I should apply the flux, electric flux through the Gaussian surface is given by this expression. Now guys, what is Q enclosed signify? What does my Q enclosed signify? The Q enclosed signifies the total net charge, right? Net charge inside system. Okay. So how many options have this? Option A, yes, it involves charge. Option B, it doesn't involve charge. Option C, yes, it involves charge. Option D, it doesn't have anything. So what does this epsilon signify? Now, what is epsilon, guys? We had learned this in our very early classes of this same chapter. What is epsilon? Yes, correct, Prakash. Yes, what is epsilon? But I'm asking, what is an epsilon? What do we represent using epsilon? Yes, correct, Prajwal. Yes, we derive, okay, we give epsilon as permittivity. Okay, it's what is permittivity again, guys? It's like, is it like how much it allows or how much it opposes the charge to pass through it? Oppose or allow. What is permittivity? Permittivity means it's a materialistic property. Okay, yes, it's a materialistic property. So it shows how much an object or how much a medium opposes the flow of or opposes the allowance of any charge passing through it, right? So epsilon is combination of two words, that is it's the combination of two functions, epsilon r times of epsilon naught, where epsilon naught is absolute permittivity and epsilon r is relative permittivity. So yes, this signifies the material medium. Okay. So option C would stand better in this case. My electric flux depends both on charge enclosed as well as the material medium. So option C will be the correct answer. So everyone, very good. Whoever answered this, very good. So everyone who did not get, don't worry. You got the halfway correct, right? So now you are full way correct. You learned a new thing if you have given the wrong answer. Cool. So yes, any doubts in this, guys? Please let me know if you have any doubts in this particular concept. We shall move. Okay, cool. So next we'll study in today's class, we'll be starting with applications of Gauss's law. So why do we apply Gauss's law? Where do we apply Gauss's law? In our very previous class of Gauss law, we had learned that the application of Gauss law is to find the electric field. So where do we want to find the electric field? We want to find the electric field, say in cases of continuous charge distributions. So guys, if you remember, when we were trying to find the continuous charge distribution, so we are trying to find the electric field due to a infinitely long conductor. How was that? So it was very tedious, right? So we had to take this, we had to find x, we had to find theta, then we had to find d theta, then we had to use trigonometric functions, then we had to integrate. So it was a lengthy process. So Gauss's law helps us to eliminate this lengthy process by just using its single math function. Okay, so we'll check how it would help. Okay, so first case, we'll study about solid sphere. So let's consider a solid sphere. So how does a solid sphere look like? Say if I have solid sphere which is completely charged, say assume I have a solid sphere which is completely charged, how would it look like? It looks something like this. Say it is having some charges, say it's positively charged. So all the positive charges, what happens? All the positive charges, the electric field lines from positive charges always emerges out, right? Yes. So these electric field lines are emerging out. These these arrow-like structures are the electric field lines which are emerging out of a solid sphere which is charged with the positive charges completely. Now what happens? So can we draw the equipotential surface for these electric charges or electric field? Can I consider the equipotential surface here? How does it look like if I want to consider the equipotential surface? So how can I draw the equipotential surface? If I go parallel to the direction of electric field, if I go parallel to the direction of electric field, I'll find my potential remains constant, right? So I'll find my potential remains constant throughout this. So I'll find an equipotential surface. Now equipotential surfaces, these equipotential surfaces behave as an enclosed surface. Okay, guys, this is very important. Please listen carefully. These equipotential surfaces behaves as an enclosed surface to this solid charge sphere. Understood? Artha aita? So in case of a charged solid sphere, the field is emerging out in all directions, and this creates an equipotential surface. So you could see this is the equipotential surface. Now these equipotential surfaces, say this red color ball which we had here is my charged sphere. Now this red color ball is inside a green color ball. If you could see here, this red color ball is inside a green color ball. So this red color ball is nothing but my charge sphere. Now this green color ball or the yellow color ball is my equipotential surface. Now how these equipotential surface behave as? These equipotential surface behave as the closed surfaces. Okay, behaves as closed surfaces. Okay. So now, can I apply Gauss law for this? Can I apply Gauss law for this? Yes, we can consider such equipotential surfaces as closed surfaces, and we could consider an area vector in it to apply Gauss law. Any doubts in this, guys? Why do we require equipotential surfaces and how we apply Gauss's law? Please reply if you have understood. Yes, click on yes. If you have not understood any point, please ask by clicking on no. If you have any doubts, please raise your hands and you could ask. Okay, yes, cool. So hope everyone have understood why we require equipotential surfaces and how we can apply Gauss's law. Yes. So now, say again, we are coming to two cases. We have two cases in the case of solid sphere. Say first case is we'll try to find the electric field outside the solid sphere, say at a point r which is greater than the radius of solid sphere. Okay, so let us consider a solid sphere of radius r. Say I have considered a solid sphere of radius r. Now I'll consider its equipotential surface of radius small r. In this case, my radius small r is greater than the of capital R. Okay, now what should I consider for Gaussian for applying Gauss law? I should have two conditions. What are the two conditions, guys? Like we discussed in earlier, what are the two conditions? So first condition is we have to consider dA in such a way that my electric field is always uniform. Okay. Then second condition is my dA should be such that my electric field is either parallel or anti-parallel to it, parallel to area vector. Okay, these two are the conditions. So if I consider an area vector dA, so if I consider an area vector dA which has a electric area vector, if I consider an area vector dA, then it has its direction along n cap direction, which is always outwards, right? It's always outwards. Now if I try to find, say this sphere which I'm considering here is completely charged with capital Q. So it's a volume charged sphere. Okay, so this is a solid sphere which is charged with volume charge density rho. This sphere is charged with volume charge density rho, and let Q be the charge on this surface. Say, let me consider this entire charge. The entire sphere is charged with the charge of capital Q with the volume charge density of rho. Then the cos theta. See what happens here, guys. In this case, my electric field will emerge out in all directions, right? So what happens? My electric field will emerge out in all directions. Then my electric field will be in parallel with the area vector. Say if I consider an electric field here, my electric field will be in parallel with area vector n cap. Then my cos theta value will be 1. Now if I apply Gauss law, what happens? Say I'll try to apply Gauss law using this expression. Phi is equals to integral E dot dA or EdA cos theta. So my cos theta value will turn out to be 1. That is equals to Q enclosed by epsilon naught. Okay, understood till here? Yes, guys, please click on it. Someone, yep. Next, we'll try to simplify. See, my cos theta, since my theta is equals to 0, since my theta, the angle between E and n cap is 0. So what happens? My cos theta tends to 1. Now, the remaining things which I have is E dot dA is equals to, I'll substitute my value of charge Q enclosed inside this Gaussian surface. So guys, this is my Gaussian surface. Remember, the equipotential surface will become my Gaussian surface. Now the Q enclosed inside this Gaussian surface is Q, capital Q. So I have substituted the value of capital Q divided by epsilon naught, since it's kept in a vacuum or air medium. Now the electric field emerging out of this charge sphere is constant or uniform. So what can I do? Can I remove this out of the integration? Can I remove that electric field out of the integration? Yes, no, please reply. If my electric field is constant, can I remove this electric field out of the integration here? Yes. Then what happens? If I try to remove that, I'll get E. I'll remove the electric field outside. I'll get E times of integral of dA is equal to Q by epsilon naught. Now, guys, tell me, what is integral of differential of this function A? Integral of differential of function A is, or if I integrate dA, if I integrate dA over the entire function, what would I get? I would get area A, right? So my expression then becomes integral of E dot dA, or E into integral dA is equal to Q by epsilon naught. This on substituting the value of A. So what is my value of A? Area of sphere. Area of sphere is 4 pi r square, right? So I'll substitute that. Then yeah, I'll get my E is equals to Q by 4 pi epsilon naught r square in the direction of r cap. So guys, which formula is this? Yeah, the formula though. ER is equals to Q by 4 pi epsilon naught r square in the direction of r cap. Which formula is this? Have you seen this formula earlier? So we got this formula finally. So this is the expression we get for electric field of a sphere enclosed inside a closed surface. So which formula is this? I want you guys to guess, or if you know, please tell me. Forgotten? I'm waiting for answer. No, Prajwal. E is equals to K times of Q by R square. This, if you have forgotten, this is nothing but E is equals to K times of Q by R square. Which formula is this? Yes, correct, Ramakrishna Reddy. So this is the expression for electric field due to point charge. Remember. So this is the expression for electric field due to point charge. So by this we can consider all my regular objects which are completely charged, which are uniformly charged as point charges. Okay. So yes, if I try to apply, say if I try to apply my electric field expression, and guys, if my Q, see, if my charge Q is not given directly, if they give my Q in terms of volume charge density, what is volume charge density, guys? Again, please tell me, what is my volume charge density? It's given by rho is equals to, yes, Krish Modi, correct. Volume charge density, rho is equals to, yes, it's Q by volume, right? Q by volume, correct, Prajwal. So that's what we are trying to say. If Q was not given and only rho is given, then we can write Q as Q is equals to 4 by 3 pi r cube times rho. Then we can try to simplify this expression for electric field as E is equal to, substitute the value of Q here, we'll get 4 pi by 3 r cube by rho. So from here I can cancel my 4 pi. Anything else, guys? Anything, can I cancel anything else? No. So I can write electric field for point charge, or sorry, the electric field due to solid sphere at a point outside the sphere, as E is equals to rho r cube by 3 epsilon naught r square in the direction of r cap. This is the expression for electric field. So how many steps did it take, guys? How many steps did it take? It did not take tedious integration. It did not take tedious trigonometric functions. It just took only 2 steps actually. So phi is equals to q by epsilon naught. Substitute the value of q, you would get the electric field value. That's it. So this is the expression for electric field using Gauss's law. So this made the Gauss law made the electric field derivation very easy. Okay, got this, guys? Any doubts in this? Got this expression, everyone? Any doubts? So this is the expression for electric field. Okay, again. So what happened? So in our previous expression, we had my electric field. So when I try to substitute the area of this sphere, so when I try to substitute the area of sphere, we got E times of area, that is 4 pi r square area of sphere. So we get E is equals to Q by, so I cross multiplied this area of sphere to the denominator. I got E is equals to Q by 4 pi epsilon naught r square. Okay, this is general expression which I get for electric field of solid sphere in terms of Q. Okay, so this is also similar to the electric field due to a point charge. Okay, yes. So this is the general expression which I get for electric field. Suppose if Q is not given, if the value of charge distributed is not given directly, and if they mention it in terms of volume charge density, if they mention in terms of volume charge density rho, then I can write my Q as, we know rho is equals to Q by 4 by 3 pi r cube. Okay, this is the volume of sphere. If I try to substitute from here, I'll get Q as, I have to cross multiply this, that's it. Q as 4 by 3 pi r cube times of rho. Okay, then if I substitute this value of Q in the expression of electric field, E is equals to K times of Q by R square. So I would get, yes, I would get 4 pi by 3 r cube times rho by 4 pi epsilon naught r square. From here 4 pi cancels. I'll get the expression for electric field due to solid sphere outside its surface as E is equals to rho times of r cube by 3 epsilon naught r square. So this is another expression for electric field in terms of surface charge density. Artha aithamma? Any doubts, guys? Yes. So we'll try to solve a question. So guys, yeah, any doubts? If you have any doubts, please let me know. I'll wait for 20 seconds if you have any doubts. Okay, 20, 19, 18, 17, 16, 15, 14, 13, 12, 11, 10. Please ask any doubts. If you have any doubts, please ask. 5, 4, 3, 2, 1, 0. Okay, no doubts. At least no doubts. If you don't have any doubts, yes. Okay, let's. Okay, then I'll try to give you a question. So this is a question for you to think, guys. Can you see this figure here? I hope everyone is able to see this. Can you see the figure here? Yes, yes. So what's happening? So I have considered a closed surface here and a conducting sphere here. Okay. So I have a conducting sphere and a closed surface. Now at point P, if I bring a positive charge, say if I bring a positive charge at point P, then the flux through the the flux of the electric field through the closed surface is. So what happens to the flux inside this closed surface? This is the question. Try to answer, guys. ಅರ್ಥ ಆಗಿದ್ರೆ ಈಸಿಯಾಗಿ ಬರುತ್ತೆ ನೋಡುವ. How many of you can try? I mean, how many of you can answer correctly? Excuse me. Okay, I have launched a poll for everyone in Zoom. Cool. So far out of 3 students, only one had given me the right answer. In Zoom, only one had given me the right answer out of 5. So guys, please try to check, think, apply all the basics. Yes, Manju, correct. ನೀವೇನ ಕೊಟ್ಟಿದ್ದಲ್ಲಿ ಮಂಜು ಪೋಲಲ್ಲಿ ಕೊಟ್ಟಿದ್ದು ನೀವೇನಾ I don't know, but Manju, your answer is correct. Manju RM. Oh, cool, super. YouTubers, please try to answer. Come on, guys. See everyone. Hope you could answer this. So guys, yes, mega correct. So guys, surprisingly, only 2 out of 11 students have given me the right answer. Okay, 3 out of 13 students have given me the right answer. Please guys, try to answer now. Don't challenge and togoli. Ramakrishna, no. Amod, no. Amit, correct. Okay. No, Prajwal. So this is a food for thought question. I guess it will go something like that. Prajwal EM, correct. Prajwal, yes. Check ಮಾಡಿ. Prajwal EM, correct ಇದೆ. Rakesh, check ಮಾಡಿ. So here, Krish Modi, check your answer. So guys, okay, I'll wait for more 20 seconds. So after that, I'll discuss the question, okay? Try, come on, it's good. So far, out of 15 students, 4 students have given me the right answer in Zoom. And in YouTube, okay, I have to wait. Rakesh, Allah, check ಮಾಡಿ. Okay, so no Agnes. Rakesh, correct. No Krish Modi, no Agnes. Krish Modi, no. Okay guys, so I'm going to end the poll. Let's check. Okay, so guys, tell me what happens when I bring a positive charge. Okay, yeah, when I bring a positive charge near a metal conductor. Say this is a positive conducting sphere, right? So when I bring a positive charge, yes, Amod, correct. So when I bring a positive charge near this metal conductor, this is my conducting sphere. What happens? This is a positive charge. Please reply. What happens when I bring a positive charge near a conductor? What should happen, guys? So is my conductor always neutral? My conductor is always neutral, right? So the net positive charge and net negative charge remains the same. True or false? Reply, guys. Come on. Everyone, please try to reply. So my total charge inside a sphere, inside a conducting surface, will be always net electric field or net charge inside a conducting surface will be 0. Right? Correct. True. So when I bring a positive charge here, what should happen? What should happen ideally? Or what should happen really? So this is a positive charge. So what happens to all positive charges present here? So initially there were positive, negative, positive, negative, positive, negative, positive, negative. So there were all sorts of plus and minus charges. So what happens then? Okay. Positive, negative, positive, negative, and positive, negative. So what happens? Which moves away? Which moves away? So what happens is all the positive charges are pushed away. Why? All the positive charges are pushed away towards one end, and all the negative charges are attracted, right? You see, all the positive charges are repelled away from this negative charge. Positive charge, and all the negative charges are attracted towards it. Now, if you see the closed surface, guys, if you see the closed surface, what happens to the Q enclosed inside this closed surface? What happens to the Q inside this closed surface? Come on, guys, tell me now. What's the answer? What happens to the Q enclosed inside the surface? See, my Q enclosed inside the surface is positive, right? There are lots of positive charges accumulated inside this surface. So the flux of the electric field through the closed surface will become positive. That's it. So option B is the right answer, guys. So everyone who had given me the right answer, congrats. And everyone who had not given, you are just tiny bit close away to the answer. But yeah, next time we could try. Okay. So hope everyone had understood how the electric field of sphere was calculated. Now we'll consider the electric field of solid sphere again. The case 2. So we'll consider the solid sphere. Now we have to calculate electric field inside the solid sphere. So in the previous case, we had calculated the electric field outside the solid sphere. In this case, we'll be calculating the electric field inside the solid sphere. So again, we have to consider a solid sphere of radius capital R. In this case, my capital R is bigger than small r. Now I'll consider another sphere of radius small r inside my capital R. I mean, inside the sphere, inside the bigger sphere, I'll consider a smaller sphere of radius small r. Now, what's the charge enclosed or what's the charge inside this bigger sphere? So guys, initially my bigger sphere is the one which is having the charge, right? Which is having the volumetric charge rho is equals to Q by volume, that is 4 pi capital R square, yes. So this was the volume charge density enclosed inside this bigger sphere. Now, if I want to calculate my electric field inside this bigger sphere, so what I did, I tried to find a point R, or I try to find a, inner sphere of radius small r. Now, I have to consider small area vector dA such that, so I have to satisfy two conditions such that my electric field is constant or uniform through this small surface area, and my cos theta, it's also symmetric. See, if I try to integrate this entire sphere, I'll get the, if I try to integrate this entire area, I'll get the entire sphere area, right? So it's also symmetric. Now, what happens to the cos theta value? Guys, what happens to the cos theta value again here? Reply please. What happens to the cos theta value? My cos theta value will become equal to 1. Why? Cos theta will be equals to 1. Why? Yes, my direction of electric field emerging out. See, since this is still a solid sphere, my direction of electric field emerging out is always parallel to that of area vector, right? So yes, correct, Harsha. So my cos theta value will be 1. Then how can I write my Gauss law? My flux phi is equals to Q enclosed by epsilon naught. My phi is nothing but E dot dA, integral of E dot dA. Now on simplifying, then Q enclosed is given by Q by 4 pi, so Q by epsilon naught. So we know that rho is equals to Q by volume. So Q will be rho times of volume, right? Q will be rho times of volume. So I've directly applied, since we had checked this condition in our previous case. So we have directly applied this. So I'll get Q is equals to 4 by 3 pi r cube times of rho, where 4 by 3 pi r cube is my volume. So this will be my volume. Then substituting the values of area and charge, I would get E dot A is equals to 4 pi r cube into rho by 3 epsilon naught. Guys, what happens here? See, I substituted the value of A. So on integrating, E integral of dA is equals to, with area A, rho 4 pi r cube by 3 epsilon naught. If I try to simplify this, I'll get this expression, right? So integral of differential of dA will be my A. So I got my area A as area of sphere is 4 pi r square. So I'll try to simplify that. So if I try to simplify this small area r, what would I get, guys? Please try to simplify and tell me the expression. Tell me the final expression. Yes, Krishna. Cool. So my 4 pi cancels. Can I cancel my R2? Can I cancel my R square and R cube? Yes, no, something please reply. R square ಮತ್ತೆ R cube cancel ಮಾಡ್ಬೋದಾ? ಹೌದು, yes. Yes, R cube ಮಾತ್ರ cancel ಮಾಡ್ಬೋದು. I'll get one R remaining. So I'll get E is equals to R rho by epsilon naught, is it? So this R rho by epsilon naught into 3. This is my expression for electric field inside a solid sphere. Okay. So I get expression E is equals to rho R by 3 epsilon naught. So guys, now one more, see one more thing. So in this expression, I had rho R by 3 epsilon naught times R cap. So I multiplied R and R cap to get this R vector. Okay. So this is my expression for electric field. Yeah, I'll try to repeat that again. So what I did, so had integral of E dot dA is equals to rho 4 pi R cube by 3 epsilon naught. So this is nothing but my Q in terms of volume charge density, right? So I know that the electric field is constant. So I removed this electric field out of the integration. So I got E integral of dA is equals to rho 4 pi R cube by 3 epsilon naught. So my integral of differential of A is nothing but my area. So E times of area is equals to 4 pi R cube times rho by epsilon naught. So from here 4 pi cancels, R square and 1 R, I mean R cube part. Only the cube part of R cancels. I'll be still remain with R and rho divided by epsilon naught. So okay, there was 3 also here, 4 by 3 pi R cube. So R rho by 3 epsilon naught is still remaining. So my expression for electric field will become rho R by 3 epsilon naught times R cube, R cap. So this R times of R cap will become my magnitude into direction, that is my R vector. So this is my expression for electric field due to, or this is my expression for electric field inside a solid sphere. Okay. Expression for electric field inside a solid sphere is given by this expression. Any doubts here, guys? So we got two expressions for electric field outside the solid sphere and inside the solid sphere. Okay, but what is the general expression anyways, guys? General expression for electric field of solid sphere will be nothing but k times of q by r square always. Okay, so using Gauss's law, we had checked by substituting the value of q as volume charge density times volume times rho. So we get this expression. Yes, any doubts here? Any doubts in this, guys? Please come on, tell me. Any doubts in this, or shall we move on? Any doubts in this derivation, or shall we move on? Guys, again, I'll wait for 10 seconds. Please reply. Okay, no doubts. Cool. So I have a question for everyone again. Please try to solve this question. So my question goes like this. So electric charges are distributed in a small volume. The flux of the electric field through spherical surface of radius 10 centimeter surrounding the total charge of 25 volt meter. What will be the flux over a concentric sphere of radius 20 centimeters? So the question is, say electric charge is distributed in a small volume. Say my electric charge is distributed in a small volume. Say I'll call this small volume as small v, and this entire charge distributed as q. The flux of the electric field through a spherical surface of radius 10 centimeters surrounding the total charge is 25 volt per meter. So what's happening? I have a 10 centimeter radius sphere. So I have a 10 centimeter radius sphere. Okay, this is 10 centimeters. Now, since the electric fields are emerging out of this, okay, the electric field will be straight line. So since the electric field is emerging out of this charged surface, I get electric fields in all directions. Now, the electric flux experienced at 10 centimeters solid sphere is 25 volt meter. Okay, they have given the electric flux experienced for 10 centimeters sphere is 25 volt meter. Now, if I keep the same system inside a 20 centimeter radius sphere, say I have a 20 centimeters radius sphere. Now, what is my flux in this case? Guys, come on, try to answer this. Come on, guys. This is we had solved similar question in our earlier classes. In our previous class, we had solved the same. Okay, yes, correct. Mega, correct, Manju. Please answer in the polls too, guys. Don't only answer in chat box, also answer in the polls. Mega and Manju, try to answer in the polls also. Your answer is correct. So others, guys, please try to answer. YouTubers, please try to answer. Please try to give the answer. So everyone who had attended the previous class will be having the knowledge of this question, right? So Harsha, please check your answer again. Harsha, check your answer. So far, out of 4 students, 2 students have given me the right answer. Guys, please try to answer this. No, Amit, check your answer again. Yes, Prajwal, correct. Prajwal, EM, correct. Please try to give the answer in your poll. Okay, guys, I'm going to end the poll for everyone. YouTubers, yes, Devika Rani, correct. Devika Rani, M, correct. Others, please try to answer. Okay, guys, cool. I'm going to end the poll. So most of you had given the answer as B. I don't know why, but yeah. So the correct answer is option D, guys. So guys, the answer is very simple. Answer is very simple. Krishmo, the correct answer. So guys, what is my phi? Expression for phi using Gauss's law. So that's what we studied so far, right? My expression for flux using Gauss's law is given as phi is equals to Q enclosed divided by epsilon naught. Guys, correct? Is this my expression? Is this my expression? Yes, my electric field is constant. Yep, correct, Devikrani. So my electric field is constant, my area vectors are constant, right? So my flux depends only on the charge enclosed inside the closed surface and only on the material medium. Does it depend on area here using Gauss's law? Is it depending on area? Is my flux changing with respect to area or radius or any other thing? No, right? My flux changes only based on the enclosed charge. So I have only a charge of Q inside this sphere of radius 10 centimeters. At radius of 10 centimeters, if it has a flux of 25 volt meter, say if I remove this outer surface and if I keep it inside, if I keep the same charge inside a 20 centimeter surface also, my flux will still be Q enclosed by epsilon naught, provided my epsilon naught is same in both. The permittivity is same or the material medium inside this 10 centimeter radius sphere and the permittivity of material inside the 20 centimeters radius sphere, if both are same, then if I am keeping the same charge Q, then the flux will be given as Q enclosed by epsilon naught for both the cases. Say in first case also it will be Q enclosed by epsilon naught, that will be 25 volt meter. In second case also it will be Q enclosed by epsilon naught, that will also be 25 volts meter. Okay. Yes. So that's why my answer is 25 voltmeter. Any doubts in this, guys? So one more explanation which we had given earlier is, yes, my electric field varies as a function of 1 by r square, whereas my flux varies as a function of electric field times area. Here my area varies as a function of r square, right? So if I try to write my flux, it varies as 1 by r square times of r square. So these cancels. My flux doesn't depend on area or electric field here. It only depends on the charge enclosed. Okay, understood, guys? Please let me know if you have understood, or if you have any doubts, let me know. Hi guys, please be active. Please try to respond. Everyone. Your response gives me power. Okay. You know, Power Rangers, it's something like that. Okay, no doubt. Okay, cool. Understood, right? Okay, next. We'll try it. Okay, next I have one more question for you guys. Please try to solve this question. A spherical volume of radius 10 centimeter contains a uniformly distributed charge density of 2 into 10 power minus 4 coulombs per meter cube. Find the electric field at a point inside the volume at a distance 4 centimeter. So we had just derived an expression, right? We had just derived an expression for electric field inside a sphere. So please try to use the same formula to find this. You could try to find this. A spherical volume of radius 10 centimeter contains uniformly distributed charge of density. What is given? Charge density rho is given. Rho is 2 into 10 power minus 4 coulombs per meter cube. Rho is given. And radius, volume of radius r is given of the sphere. Now what is volume? V is equals to what? You have to find that first. Then find the electric field at a point inside the volume at a distance 4 centimeters. So they are asking you to find, say, if capital R is 10 and small r is 4 centimeter, find my electric field. So guys, you could directly try to substitute the values in the given equation, or you could try to derive again. If you remember, please try to apply it. Correct, Manju? Manju, correct amma. So polls launch ಮಾಡ್ತಿದ್ದೀನಿ, ದಯವಿಟ್ಟು ಇದರಲ್ಲೇ ಆನ್ಸರ್ ಮಾಡಿ. Everyone please try to answer. Everyone in Zoom try to answer in polls. Everyone in YouTube please try to answer in your chat box. Okay, correct. So Manju, ad ನೀವೇನಾ ಹಾಕಿದ್ದು? Okay, cool. So others please try to answer. ಜನ ಆನ್ಸರ್ ಮಾಡಕ್ಕೆ ಟ್ರೈ ಮಾಡಬೇಕು. ನೀವು ಟ್ರೈ ಮಾಡಿ ನೋಡಿ, ಅದು ಸಿಂಪಲ್ ಸಬ್ಸ್ಟಿಟ್ಯೂಷನ್ ಇರುತ್ತೆ, ಮಾಡಿ ಬರುತ್ತೆ. So everyone in YouTube also please try to answer this question. I hope everyone will be able to just substitute the values in the given expression, so which we derived earlier. Then once you are done, you will get the answer. That's it. So whoever gave the answer right now in the poll was wrong. Please check your answer. So poll ನಲ್ಲಿ ಯಾರೋ ಆನ್ಸರ್ ಮಾಡಿದ್ರಲ್ಲ, ಅದು ತಪ್ಪಿತ್ತು, ಚೆಕ್ ಮಾಡಿ ಮತ್ತೆ ಇನ್ನೊಮ್ಮೆ. Yes guys, come on, try to answer. So only 3 out of 27 plus students have answered. Guys in YouTube, please try to answer. You could either derive an expression or you could directly solve this. So no guys, no Krish. Yes, Krish Modi correct. Sorry, Krish Modi correct. Others please try to solve. Mega, check your answer again. So what's given, guys? My rho is given as 2 into 10 power minus 4 coulombs per meter cube. My distance, where I have to check my point, or where I have to check my electric field, is given as r is equals to 4 centimeters. That is nothing but I can write it as 0.04 meters. So try to find the electric field. So guys, what's the expression we got? If you know the expression, please try to substitute directly. If you don't know, you could also try to check that expression. So if somebody have tried, written this expression, please try to substitute directly. EP is equals to rho times of R by 3 epsilon naught. So this is it. So this was the expression which we derived. Guys, plug in the values, you'll get the answer. That's it. EP is equals to what is rho? 2 into no omega. Omega value, please check your answer. Omega 2 into 10 power minus 4 times of what is R? R, again guys, you can use the simplification which is given here. So they have given, take 4 by 8.85 as 0.45. So you could use this values, or if you have good math skills, you could also try to find directly. So I'm taking to the next page. So EP will be equals to rho times of R by 3 epsilon naught. So this will be 2 into 10 power minus 4 times R is 4 centimeters, 4 into 10 power minus 2 divided by 3 into 8.854 into 10 power minus 12, right? Now guys, everyone please try to solve only this. It's Saku. Okay, I have in the poll. So most of you had got some different answer. I don't know how. Please try to solve this. You'll get the answer. So 2 fours are okay. 4 by 8.85 is given as 0.45. 0.45 into 10 power minus 2. Okay, divided by 3 into 10 power minus 12. Okay, guys, come on, solve this. What is 2 into 0.45? 45 twos are. What is 45 into 2? It at least here draw. 45 into 2 90 ಅಲ್ವಾ? So 2 into 0.45 will be my 0.9 into 10 power minus 4 into 10 power minus 2 divided by 3 into 10 power minus 12. ನೋಡ್ರಪ್ಪ ಇದನ್ನು ಸಿಂಪ್ಲಿಫೈ ಮಾಡ್ಬೋದಾ ಸಿಂಪಲ್ ಆಗಿ? Try to simplify this, everyone. Yes, correct, Amod. Try to simplify this. ಏನಾಗುತ್ತೆ? So if you take this into the numerator, you'll get 10 power 12, 12 minus 2, 10, 10 minus 4, 6. 0.9 into 10 power plus 6 by 3. So if you try to simplify 9 into 10 power 5 by 3, ಎಷ್ಟಾಗತ್ತೆ? ಎಷ್ಟಾಗತ್ತೆ ನೋಡಿ? 3 3s are 9 ಅಷ್ಟೇ. Electric field inside the point EP is 3 into 10 power 5 newtons per coulomb. ಮುಗಿತಲ್ಲ? Or newtons per coulomb ಆಗಲ್ಲ ಅಂದ್ರೆ volt meter square per coulomb. ಹೌದಾ? Okay, it's newtons per coulomb. So option A is the right answer, guys. So ಅರ್ಥ ಆಗಿತ್ತು ಅನ್ಕೋತೀನಿ. Any doubts? So this is direct substitution, guys. Nodi, it was the direct substitution if you remember the formula. YouTubers, yes, Ramakrishna already got it correct. Others, guys, please try to respond. If you have any doubts, let me know. Any doubts so far, guys? Okay. So if no doubts, we'll go to next concept. That is application of Gauss law for infinitely long charged wire. So what I have, say I have an infinitely charged wire. Say what I'll do. So this infinitely charged wire will have what type of density? Linear density, volume density, or surface density? ಯಾವ ತರ ಚಾರ್ಜ್ ಡೆನ್ಸಿಟಿ ಇರುತ್ತೆ? ಲೀನಿಯರ್, ವಾಲ್ಯೂಮ್, ಸರ್ಫೇಸ್? Yes, it will be having a linear charge density that is given by which? Lambda, sigma, or rho? It's given by lambda. Wow. Yes. Now say if I have such electric field lines emerging out. So if I try to draw the potential surfaces, equipotential surfaces, what I would get? What I would get if I try to draw the equipotential surface for this linear charge density? What I would get if I have to draw the linear, surface, equipotential surface for this linear charge densities or infinitely long current carrying conductors? ಯಾವ ತರ ಬರುತ್ತೆ ನನ್ನ equipotential surface? How would I get my equipotential surface as? ಹೇಳ್ಬೇಕು. So if I try to join them, so the infinitely long current carrying conductor as the electric field emerging out in all directions, then if we try to connect the phase of this, if we try to connect the equipotential surfaces, we will get cylinders, ಆಯ್ತಾ? So ಯಾವ ತರ ಬರುತ್ತೆ ನನಗೆ equipotential surface? My equipotential surface will be the concentric cylinders. Okay, equipotential surfaces will be concentric cylinders. Say such equipotential surfaces can be considered as area vector in this case. Now guys, it's same thing which we are going to solve again. Say consider an infinitely long charge current carrying conductor. Okay, say if lambda, so this is of infinite charge, so it's infinitely long. Now if I have lambda as the charge density, if I have lambda as my charge density, then say if I consider an equipotential surface, what happens? My charges emerges out in all directions, right? So as seen in that previous animation or in the picture, my electric field emerges out in all directions. If I try to consider one point, say I'll get an equipotential surface, something similar to this. Now guys, tell me what are the directions where my electric fields can pass through, or what are the flux? What are the surfaces I see in this cylinder? How many surfaces does this cylinder have, or how many surface, or how many surfaces? How many surfaces does this cylinder have? ಈ ಸಿಲಿಂಡರ್ಗೆ ಎಷ್ಟು ಸರ್ಫೇಸ್ ಇದೆ? Yes, it has 3 surfaces, right? So what I'll do, I'll consider my okay, if the length of this cylinder is L, and I should consider its radius as R, the radius of the cylinder as R, then I have 3 surfaces. So all the 3 surfaces will have 3 flux. Okay, all the 3 surfaces will have 3 flux, that is phi 1, phi 2, and phi 3. So I have 2 plane surfaces. I have 2 plane surfaces which are phi 2 and phi 3, and I have one curved surface. I have one curved surface and 2 plane surface. Okay, phi 1 and phi 2. Phi 1 is my curved surface, and phi 2 and phi 3 gives the flux through the plane surface. Now the net flux through the cylinder, or the net flux through the cylindrical surface, is given as summation of all fluxes. What is the net flux, guys? Say if I have electric field emerging out in all directions, say I'll be having flux, right? I'll be having flux phi 1, phi 2, phi 3 for 3 surfaces. Say the net flux would be given as phi is equals to phi 1 plus phi 2 plus phi 3. Now the flux phi 1 is due to the curved surface, and phi 2, phi 3 are due to the plane surfaces. Now what can we tell about this? So we have to consider the 2 conditions. What are the 2 conditions, guys? We have to consider the 2 conditions. Yado. So I have to consider the area vector, right? So in this condition, I have to consider my area vector. How to consider the area vector? So to consider area vector, I had two conditions. What is the first condition? When I consider my dA, my electric field should be uniform through that. This is my first condition. Second condition is dA should be such that my electric field is parallel to area vector. Okay, these are the two conditions. Howda? So with this, the electric field due to the conductor is perpendicular to the curved surface. Howda? See, my electric field due to the conductor is always perpendicular to this curved surface, right? It's not going in this direction. It's not going in this direction. It's not going in this plane direction, but it's always going in which direction? To form the equipotential surface, it's always going in perpendicular direction of my curved surface, right? Hoda. Then I should consider a small area vector dA along the curved surface of surface area dA with an n cap direction, which is always outwards. Now the flux, applying Gauss's law, we can apply Gauss law. The flux is nothing but phi is equals to integral of E dot dA. If we try to simplify, we'll get phi is, or flux phi is nothing but closed integral of ER times of dA. Why ER, guys? Why only ER? My electric field is moving outside in the direction of R. Okay, ER times of dA. Now, the electric field is thus derived as phi is equals to integral, closed integral of E dot ER dot dA. That will be equals to Q enclosed by epsilon naught from Gauss law. Then ER into integral. Since my electric field is constant, my electric field comes out of the different integration. I'll get ER integral of dA is equals to enclosed by epsilon naught. So integral and differential of this dA will be the area of the surface area. Here, guys, it should be the surface area of what? Cylinder. So what is the surface area of cylinder, guys? How can I construct a cylinder? I can construct a cylinder by considering two circumference 2 pi r, two circles of 2 pi r at a separation of length L. So this is my cylinder. I have 2 pi r times L. Say if I take a circle of circumference 2 pi r and move it along the radius, move it along the length L, I would get a cylinder. ನಾನೊಂದು 2 pi r ರೇಡಿಯಸ್ ಸರ್ಕಂಫರೆನ್ಸ್ ಸರ್ಕಲ್ ತಗೊಂಡು ಅದನ್ನ ಲೆಂತ್ ಎಲ್ ಅಲ್ಲಿ ಎತ್ಕೊಂಡು ಹೋದ್ರೆ, ಇಫ್ ಐ ಟೇಕ್ ದಿಸ್ ಸರ್ಕಲ್ of 2 pi r circumference towards, if I lift it at a length L, will I get a cylinder? So that area will become my surface area of cylinder. So I have substituted all the values. Now what is my electric field, guys? My electric field will be E is equals to Q by 2 pi RL times of epsilon naught. Again, guys, if my Q is in terms of lambda, so what is lambda? Lambda is equals to Q by L. Now Q will be equals to lambda times of L, right? So if I try to substitute this, we get Q enclosed is lambda by, Q enclosed is equals to lambda times L. Then we get electric field E is equals to lambda times L by 2 pi RL times epsilon naught. If I try to simplify this, what's happening? My L and L cancels. I would get the expression as E of R is equals to lambda by 2 pi R epsilon naught. See how easy it was? So this was the same expression which we had derived earlier for infinitely long current carrying conductor using trigonometric functions, using the integrations, using all other functions. So this was very simple to find the expression for electric field due to an infinitely long current carrying conductor using Gauss's law. Yes, guys, this is the expression for electric field. So again, the steps goes like this. So I had to find my flux using phi is equals to integral E dot dA, ER dot dA is equals to Q enclosed by epsilon naught. again then I have to find my area. So since my electric field is constant, I take out of the integration, then integrating over the entire surface area, I would get the surface area of cylinder. By substituting the value of surface area of cylinder, I get ER times of 2 pi RL is equals to enclosed by epsilon naught. Now if my Q enclosed is written in terms of my linear charge density, then Q enclosed will be equals to lambda times of L. Now, if I try to substitute that back in this equation, previous equation, I'll get E of R is equals to lambda L by 2 pi RL times of epsilon naught. LL cancels. So I'll get ER is equals to lambda by 2 pi epsilon naught R. So this is the expression for my electric field due to an infinite charge current carrying conductor. So this we had derived using trigonometry earlier. Now we had derived the same expression using Gauss's law. So understood, guys? Guys, understood this? Any doubts in this, guys? Please let me know if you have any doubts. Yes, no, something, please reply. Doubt ಇದೆಯಾ ಇಲ್ವಾ ಏನೋ ಹೇಳಿ. ಅರ್ಥ ಆಗಿದೆಯಾ ಇಷ್ಟು? So these derivations might be asked in your CBSE exam. So these derivations are only in point of your CBSE exams. So guys, I have a concept test for you guys. Please try to answer this concept test. So Zoom guys, yeah, you could start giving this feedback also. At the meantime, you could try to answer this question, guys. Come on, try to answer this question. So I have this question. The question goes like this. Say a Gaussian surface S1. So I have two surfaces. A Gaussian surface S1 passes through 2 point charges. Say first there is 1 point charge, another point charge, and my Gaussian surface passes through this. My Gaussian surface is a closed surface is passing through this. So I have, I'll try to draw this with a different ink, so that way we can try to differentiate. So I have my closed Gaussian surface here. So I have one charge here, one charge here. So can such Gaussian surface exist? This is one condition. So second condition is I have another Gaussian surface S2 passes in between a continuous line charge. Say I have a continuous line charge. Okay. Now my Gaussian surface exists such that, okay, I'll try to draw. My Gaussian surface S2 passes in between a continuous line charge. So it passes between a continuous line charge. So this line charge makes a hole. So assume we could assume that it makes a hole through this Gaussian surface and passes through this. Which of these two is possible? Which of these two surfaces exist in nature, in real? Or yeah, this is the question. Everyone could try to answer me in your chat box for now. Please try to answer in your chat box only. Okay. Rakesh, no. Check your answer, Rakesh. Yes, Arun, correct. Arun Kumar T, correct. Your answer is correct. So guys at YouTube, please try to answer. Everyone at YouTube, please try to answer. Arun Kumar correct na idu Rakesh ಸ್ವಲ್ಪ correct ಮಾಡ್ಕೋ check ಮಾಡ್ಕೋ. Others can try answering this question. Please try to answer this question, guys. Come on. So there is one more last part, guys. The last part is infinite charge conductor. Say if I have an infinite plane, whose charge is distributed throughout, how could I find my electric flux to that? So Chinmay correct? Chinmay correct, amma. So guys, come on. Devika Rani, correct. Krish Modi, check your answer. Okay, others try to answer. So guys, everyone please give your feedback. Everyone please try to give your feedback there. Prajwal, check your answer again. No. There is existence of at least one object. Correct, Prajwal. Prajwal, correct. Right. Prajwal EM Jain Mysore, your answer is right. So Ramakrishna Reddy, Krish Modi, correct. Ramakrishna Reddy and Krish Modi, now your answers are correct. Others try to answer. Manju are correct, Amma. Your answer is correct, Manju. Come on, guys. Come on. Solve this. Answer this. So for completion of this chapter, we have only one small concept left, that is infinite plane. Rakesh, check your answer again. For this chapter to complete, we have only one part left, that is infinite plane. So if that is done, then yeah, this chapter is completed. So application of Gauss law to the infinite plane is only left. Mega, check your answer. No. So guys, ಬೇರೆ ಏನೋ doubt ಇದ್ರೆ ಕೇಳ್ಬೋದು. If anyone have any doubts, you could ask me in any part so far. Prajwal Nayak, correct answer. Your answer is right. So YouTubers also try to answer. So there are only 4, okay, 6 people now. Okay, guys, come on. Mega SP. If you try to answer now, okay, your answer is still incorrect. Please try to check your answer. So ಏನಾಗ್ತಿದೆ ನೋಡಿ, what is a Gaussian surface, guys? See, this is very simple. Okay, so what is a Gaussian surface? What do you think a Gaussian surface is? A Gaussian surface should be one which is enclosed with some charge inside this. If you try to get this notation, everything else is fine, right? So what is a Gaussian surface? A Gaussian surface is the one which is an enclosed surface with some charge inside it. So in first case, can you see any charge inside the Gaussian surface? Can you see any charge inside the Gaussian surface in first case? Yes or no? Is there any Gaussian surface is there any charge inside this? No. In second case, is there any charge between here at this point? At this point, do we have any charge here? Yes. So surface 2 is possible, but surface 1 is not possible. So surface 2 can exist, but surface 1 cannot exist is right answer, option B. Option B is the right answer, guys. So everyone who had answered something else, please try to check your answer again. Okay. So this is much of it. So in our next class, we have to complete this. Or if I have time, I don't know. So option B is the right answer. A Gaussian surface can pass through a continuous charge, but it cannot pass through a point charge. This is because Gaussian surface passes through a point charge. It cannot be judged whether the point charge is enclosed by Gaussian surface or not. So as I mentioned in the previous diagram, so ನನ್ನ Gaussian surface ನಲ್ಲಿ ನನ್ನ charge ಒಳಗೆ ಇರಬಹುದು ಅಥವಾ ಇರದೇನೂ ಇರಬಹುದು. But when my Gaussian surface passes through a line charge, linear charge ಇಂದ pass ಆದ್ರೆ perfect exactly ನನ್ನ charge ಇದ್ದೇ ಇರುತ್ತೆ. Okay. So this is the answer. So last topic of this entire chapter was this. So ಸ್ವಲ್ಪ ಮುಂಚೆ ಬಂದಿದ್ರೆ I could have completed this. So we had electric field inside symmetry. So if we try to derive, if we complete this derivation, this chapter is done. We'll try to solve some questions based on this. Okay, ಒಂದಷ್ಟು questions ಇತ್ತು. After that, we'll try to take some doubt solving. Once that's done, we are good to go for test. So we can expect the chapter test for tomorrow, but no, naale iralla. So guys, tomorrow might be a holiday for you guys. Official notice is yet to come. So everyone, happy Deepavali again. So ನಾನೊಬ್ಬ ದೀಪಾವಳಿ ಅಂತಾನೆ ಹೇಳ್ತೀನಿ, ದಿವಾಳಿ ಅಂತ ಹೇಳಲ್ಲ. So happy Deepavali to everyone, all YouTubers and all Zoom audience. Happy Deepavali. So I know if we have class tomorrow, we may meet. If we don't have class, it will be notified to you guys. Okay. ದೀಪಾವಳಿಲಿ ಪಟಾಕಿ ಹಚ್ಚೋದು ಗೊತ್ತಿಲ್ಲ, ಪಟಾಕಿ ಕರ್ನಾಟಕದಲ್ಲಿ ಬ್ಯಾನ್ ಆಗಿದೆ ಅನ್ಸುತ್ತೆ. ಸಪೋಸ್ ಯಾ, ಥ್ಯಾಂಕ್ ಯು. So anything about the class would be notified to you guys. And guys, ನಾನು ನಿಮಗೆ ಇದು I have shared you the DPPs. You could go through the DPP, solve the questions, and try to answer that. Okay, cool. So okay guys, it's time for me to close the chat. I'll end this meet. Thank you for being here. So please try to give the polls. I mean, please try to give your feedback in the polls and then leave. Thank you. Thank you, Manju. Okay, go. Good. Gone case.